Hi everyone, it's me again. I'm gonna present this work from my talented colleague Zhang. SwitchQNet, optimizing distributed quantum computing for quantum data centers with switch networks. So these slides are fresh because I just received it in this morning. But don't worry, I will try my best to give a nice presentation. So my goal is to convey the background of the problem clear, and the key insights of the solution clear. Okay, so let's see. So the background is that there's a trend going from monolithic architecture to distributed quantum computing. So the reason is that monolithic quantum hardware suffers from scalability problem. So as the device size increases, we have less control over the qubits. We have more crosstalk issues. We have lower yield rate. So that's why we need to extend the capabilities of the single chip systems to multi-node architectures with distributed quantum computing. So recently, there's an emerging architecture called quantum data center. So in contrast to the long-range quantum networks across the cities, which is like the ultimate future of distributed quantum computing, this quantum data center aims to connect multiple QPUs within a local range of single room or facility, and focuses more on the computation need instead of the communication. So the role that the quantum data center plays is like the role EFT plays between the NISC and FTQC, I would say that. So just to draw a parallelization. So this is the what a quantum data center looks like. You can see that these orange and blue rectangles are the switch, and these lines are the optical fibers between them. So you can reconfigure. The switches to change the connectivity in this network. Okay. So the advantage of this architecture is a relatively short communication distances and controlled environment, which mitigates the photon loss and the various noise source. And the second advantage is that it requires minimal additional quantum devices without requiring the repeaters and the memory qubits in the repeaters. So I would say that this is a near-term setting that with minimal quantum resources, and this is something. This is a promising architecture that we can pursue, like in the near term. But that comes with a challenge. So the primary challenge is the heterogeneous structure in the latency profile. So it's well known that for long-range quantum communication, you need EPR pairs. But the speed for generating EPR pairs within the rack, so this is called a rack where you have several QPUs, and the cross-rack generation of EPR pairs, the speed can differ drastically. So the speed, the generation speed of EPR pair within the rack is like 1 millisecond, but cross-rack it can be as long as like 10 milliseconds. And moreover, if you want to reconfigure the switch to change the connectivity in the network, then it also takes like 1 millisecond. So this heterogeneity in the latency profile is something that we definitely need to consider when we design the software for this architecture. So just to give a little bit more data. So some preliminary experiments shows that although this cross-rack communication only accounts for like less than 20%, but generating these cross-rack EPR pairs would take more than like 60% of the overall latency. And this reconfiguration of the network using the switches will account for like 30% of the overall latency. So that's definitely a large room for improvement there. So how to address this problem? We can draw some inspiration from the classical data center classical data center also has those kind of high hierarchical structures, which can usually be addressed by the strategic data prefetching. So let's see whether we can borrow that technique to the quantum setting. And the fact is that it's very hard because quantum and classical have a completely different setting. So the first difference is that in classical setting, data can be freely replicated, but in quantum, this is prohibited by the so-called no-cloning theorem. Therefore, we cannot just copy quantum states and store them on other nodes ahead of time. So prefetching the quantum data is prohibited. However, prefetching the EPR pairs is allowed. So this is the key insight of this paper. So in a typical QPU, it works like this. So it will only have a few communication qubits for long-range communication, and the rest of the qubits serves as the computational qubits. So the idea of this paper is that we can allocate several computational qubits around the communication qubits as a buffer zone to store the EPR pairs generated, and we can consume them when we need them. So how to utilize this structure? So with this structure, you have buffer zone to store EPR pairs, and there's no need for memory qubits on the switches. Yes, so just as a comment. And so how to utilize this structure? So there are two key insights. The first one is that we noticed that there's a huge difference between reconfigure latency and in-rack EPR pair latency. So we want to prepare multiple in-rack EPR pairs whenever the optical path is available. So let me demonstrate this with a motivating example. So suppose that this is the circuit that we want to execute, and the naive solution is just whenever you want to execute a C0, then before that you generate the EPR pair on the associated nodes, and that will give you a long latency. However, if you notice that these three EPR pairs act on the same set of nodes, then we can actually generate them at the same time and just consume them when it's needed. So this can give you a saving in latency. Not too much, but meaningful. And the second observation is that the in-rack latency is far shorter than the cross-rack latency. So this is something that we want to drastically optimize. So this fact it motivates that we want to perform. We want to generate the cross-rack entanglement as much as we can whenever possible. So this is the key idea of this improvement, and this relies on a technique called entanglement swapping. So if you want to generate the entanglement between A and C, you can actually generate entanglement between A and B and C, and then fuse them together. So this idea can lead to a huge improvement. So let's see how this example shows. So suppose that at this point you have this configuration of network. So you can use this green line to generate a cross-rack entanglement between A2 and B1, and this is exactly what we need here. However, at the same time, you can also generate the entanglement between A1 and B2. But this is not what we want. We want A1 and B1 for this gate. However, we can use this so-called entanglement swapping to decompose this entanglement into the entanglement between A1 and B2, which we can have in parallel with the green one, and then use another in-rack entanglement, and combine them together. You can generate the entanglement between the two nodes that we want to act a C0 on. So in this way, we can parallelize these two cross-rack entanglement generation. and that gives a huge time saving. I think this is a smart idea. So this is the improvement on the latency side, and another key difference between the classical and quantum data center is that in the quantum setting, the system is very sensitive to noise. So in classical setting, data can be stored for a long time and can be transmitted robustly. But for quantum setting, they can decohere over time. And every communication has infidelity. So not only we need to consider to improve the latency, but also we need to consider to guarantee that this process don't introduce too much error, too much decoherence. So we need to take the fidelity into consideration as well. So how do we ensure that this process don't introduce too much error? So first we analyze that there are two major error sources. The first one is the decoherence due to during the storage. So these prefetched EPR pairs can decohere when stored in the buffer. And to mitigate this, we need to restrict the look-ahead window and not make them too large. Meaning we don't want to just store a large number of EPR pairs in the buffer zone and just wait and let them accumulate the decoherence. And the second error source is that is from this decomposition. So as you can see, when we decompose this entanglement into this one, this red one, and this in-rack one, this blue one is like an additional error source. So how to reduce the infidelity on that side? The paper proposes state distillation. So from my perspective, it's like using the space to trade for time and fidelity. So I guess this is a high-level insight. Okay, so finally we go to the evaluation. So I believe I have introduced the background and the problem and the key insights clearly. Hope that makes sense to you. And the evaluation should be like natural. So we perform the optimization on these benchmarks, and the metrics will be the overall communication latency, and the lower the better. And the second will be the number of additional EPR pairs, and the lower the better. And the third will be the average wait time in the buffer zone. And we expect that this wait time should be lower than the cross-track latency, so that we have like reduction in the total latency. So the evaluation tests a few configurations, different configurations. So we alter the number of racks, the number of QPUs in each rack, and the number of qubits in each QPU. So in these different settings, we all have similar results. So we have latency improvements, and this improvement increases as the number of qubits increases, or number of QPUs in the rack, or number of racks increases. And the second thing is the number of additional EPR pairs also increases as this number increases, but still can be at a mild level, like 10%, around 10%. And the third thing is that the additional wait time will also increase, but will still be below the cross-track latency. So these are like similar evaluation results. And finally, there's a section extending this technique to the setting with QEC. And I think I will skip that because it follows kind of the same idea. And I'm happy to take any question that I might not be able to answer.